I'd just like to do a real brief video for those of you who are not potentially familiar with the concept of dark matter. If you look at the sky, this is a famous picture called the Hubble Deep Field, where basically they pointed Hubble at a random place in the sky and took a photo for as long as they could. And what you'll notice is that there's tons of things in this picture. There's stars, there's galaxies, there's some nebula, there's all sorts of things like that. Well, it turns out that what you're actually looking at here is a tiny fraction of what the universe actually is. Most of the universe we can't detect. It's in the form of either what we call dark energy or dark matter. I'm not going to talk about dark energy for a minute. It's even stranger than what we're dealing with now. But in the case of dark matter, there's about 5 times as much of it as there is of regular matter that you take a look around and see in the stars and the galaxies and all the rest. So the question becomes, if we can't see it, how do we know that it's there? Well, it turns out that it's relatively easy to detect via other ways. If you take a look at something like the solar system, what you'll notice we have a bunch of planets going around the sun. Most of the mass of the solar system is in the sun, and then the various planets, as they go around, make orbits as they go here, or here, here's Jupiter. But as you go farther and farther away from the solar system, from the center of the solar system, the sun, basically the planets will start slowing down because the gravitational force of the sun is much less out here at Neptune, for example, than it is at Mercury. So Mercury flies around the sun very, very quickly, whereas Neptune goes around quite slowly. So we can do this. We can look at all sorts of various systems, and we can say, like, well, okay, knowing the amount of mass that's in the center of it, we can figure out how fast the various things must go around it. And we can do this for solar systems like this, but we could also do it for a galaxy. In the case of a galaxy, however, we can do the exact same thing. We can measure, for example, how fast the stars that are moving at the center of the galaxy are going versus the ones that are far out. Now, the galaxy doesn't have a strong center like the sun does. And as I said, most of the mass of the galaxy is not concentrated in a tiny little speck in the center, but there's various mathematical tricks you can do to figure out what the speed of the rotation of the galaxy should be. And what we find out is that if you do this, you should get the galaxy, as I said, the stars moving relatively quickly and then slowly falling away. So the stars out here are moving more slowly than the stars on the inside. The problem is that that's not what you see. When you look at a spiral galaxy, what actually happens is the stars out here start spinning faster, and then they keep getting faster and faster and faster. What this effectively means is that we don't know what the mass of this galaxy is. There's something else there that's causing these stars to be more strongly attracted to it and thus be able to spin faster than they would be if all we could see was the stars themselves. So there's something in here that's adding to the mass of the galaxy. And it turns out, in fact, that this is actually about 5 times more than the mass of what we actually see the stars and everything else in this galaxy. So this is where the idea of dark matter originally came from. We need to find some explanation for why these things are not behaving the way we expect them to. So is there other evidence for dark matter? It turns out that there is. The other piece of evidence that we use is something called gravitational lensing. And in gravitational lensing, light does not travel in straight lines. According to Einstein's theory of relativity, light actually is bent by gravitational forces around it. So what ends up happening is if you have something in the middle, between you and your object, like in this case we have a large and a heavy galaxy in between us, here's the Earth, or in this case the Chandra Space Telescope, and a object like a quasar, you can't see the quasar itself because the galaxy is in the way. But what ends up happening is the light from the quasar goes around the galaxy and gets bent by the enormous gravitational force that that galaxy can produce on it. So what we end up seeing when we look here is we don't see a quasar sitting in the middle of the galaxy right there. The galaxy covers that up. What we end up seeing is the galaxy with 2 stars on either side of it. And that's what these are, the quasar images. They've just been lensed by the interior of the galaxy. So we can see whether that's the case and find things like this in reality. And in fact, we can. If we go out here, we can see here's a large galaxy, and there's some stuff behind it. In one case, a quasar, which we're actually seeing, in this case, lensed 4 times. And there's also another galaxy behind it that's been lensed again. So these things are actually behind this. It's just that the enormous gravitational force that this galaxy is providing is able to bend the light around it so that the thing that's behind it actually appears off to the side. So we know this is the case. We can again look at these things. We know how much mass there would have to be here to bend the light in that direction. And therefore, we can figure out exactly how much this galaxy weighs. And then we can look at it and say, how many stars are in it? And it turns out that there are nowhere near enough stars and other stuff to make it happen. So the question becomes then, what actually is dark matter? There's been a variety of theories for this, and some of the obvious ones have been thrown out already. For example, maybe it's just things like planets and asteroids and stuff like that that we can't see. Turns out there's nowhere near enough of that stuff. Some people thought it might be neutrino mass. Turns out that's not the case. And so we've gone and tried to find more and more exotic particles that might potentially make up the 60 to 80% of the universe that we can't see. The problem with this is, and here's one of the detectors, for example, if we go to one of these detectors, in this case, this is one called Xenon. This is a quite large setup or whatever. It's tens of millions of dollars to set this guy up, and I won't get into exactly how it works, but basically this is looking for subatomic particles that could form the basis of dark matter. These things don't technically interact with very much, but we should be able to detect them in some way. The problem is that we have lots of these type of detectors that all work in different ways and are all looking at different possible combinations for what these things might be. And over again, we find nothing. So far, there's not been a single positive detection of a dark matter particle, no matter how many different ways we've looked for it. So I now have two articles for you to take a look at real quickly. One of them talking about the discovery of a galaxy that's made almost entirely of dark matter, and another one that basically says dark matter doesn't exist at all, and we need to find another explanation for everything.